A stationary source sends forth monochromatic sound. So forth, okay, the meaning of forth is away, okay. So a stationary source sends away monochromatic sound, that is sound having single wavelength. A wall approaches it with velocity 33 centimeter per second. The propagation velocity of sound in the medium is 330 meter per second. In what way and how much in percent does the wavelength of sound change on reflection from the wall? So we are asked to find in percent the change in wavelength of the sound on reflection from the wall. And we know the relation between frequency and wavelength, okay, is this. Frequency is inversely proportional to wavelength. So we have this. Clear? So we use this concept, and in this problem, we have stationary source, okay. So I'm writing, we have stationary source and we have wall, okay. So we need to understand this, and we are going to generalize this expression, okay, in this problem. And this expression is for source moving towards observer and observer moving away from the source, and the direction from source to observer is taken as positive. So as I said earlier, we are going to generalize this expression for apparent frequency in this problem. So in this problem, okay, we have a stationary source and a wall approaching towards the stationary source with velocity 33 centimeter per second. Okay, so I'm writing in this way, the frequency, okay, the frequency of sound emitted by the source changes in following two steps, because we want to find the percentage change in wavelength of the sound on reflection. So in order to find the change in wavelength, we must find the change in frequency, okay. So I'm writing, the frequency of sound emitted by the source changes in following two steps. One, okay, sound waves received by the wall, okay, and the wall, okay, acts as observer, and we have wall approaching, that is observer approaching or moving towards the stationary source. So I'm writing sound waves received by the wall, okay, which acts as observer. So this is to be noted, okay, wall which is moving, okay, which is moving towards source, and we have source at rest, okay. So we have this. So let me draw this, okay. We have source at rest. So the velocity of source Vs is 0, and let the source emit sound, okay, of frequency f, and we have wall, and wall is acting like observer, okay. So we have this, and as I said earlier, okay, the direction from source to observer, okay, is taken as positive direction. So this is taken as positive direction, and sound is always directed, okay. Sound is always directed from source to observer, and the velocity of sound, okay, v, this is 330 meter per second. So this is 330 meter per second. So we have this. Clear? And the wall is approaching with velocity 33 centimeter per second. So we have velocity of observer, that is wall, okay. V naught equals 33 centimeter per second. So we can write in SI system 0.33 meter per second. So we have this, and let the frequency of sound heard by the observer, that is frequency of sound received, okay, frequency of sound received by the wall or observer, be f dash, and f dash is apparent, okay. This is apparent frequency. So as I said earlier, we are going to use or generalize this expression for this particular case, okay, of the problem. So we have f dash, okay, this equals f and v, okay, this is velocity of sound, clear, and we have minus, and since v naught is directed opposite, okay, to the positive direction, you can see we have positive direction directed in this way, and v naught is directed opposite to it. So this direction, okay, this direction is taken as negative. So we have minus v naught, okay. So we have v minus 0, because vs, that is velocity of source, is 0. So we have f bracket v plus v naught divided by v. So let us put the value, okay. So we have f, okay, and v is 330, okay, plus v naught is 0.33 divided by 330. So let's find it, okay. So we get this, okay, 1.001 f. So we have this. Therefore, I'm writing, okay, f dash equals 1.001 f. So we have this. Let us call it equation 1. So we have this. Now, second, okay. So I have discussed this case. The frequency of sound emitted by the source changes in the following two steps. One, okay, sound waves received by the wall. So the wall is acting like observer, moving towards the source, which is at rest. Now next, okay, 2, clear. Now what you find is that the wall, okay, the wall which is observer, okay, the wall reflect, okay, the wall reflects sound, it reflects sound waves with same frequency, okay. So in previous case, okay, we have wall or observer receiving sound wave, and the frequency received by the wall is f dash. So now in next, okay, we have wall reflecting sound wave with same frequency. So what you find? Same frequency towards the source. And we know the source is at rest. So it mean, okay, it mean that wall, okay, acts as source. It is acting like source. Clear? It is acting like source. It is acting like source moving towards the source. Or let me write in this way. It is acting like wall moving towards the source. Moving towards the source, okay? And this source is real source, okay? It is a real source which is emitting sound. So what do you find? Source, and the source is at rest. So therefore, what we find is that the real source, okay? The real source. So let me write in this way, okay? The real source now act as observer. It acts as observer at rest. So we find this. Clear? So what do we find now? We have source. Okay, this is a real source. Keep in mind. Now this act as what? This act as observer at rest. Okay. And we have a wall. Clear? We have a wall and it acts as source. Okay. So we have this. And it emits sound, okay? It emits sound. So we have sound in this direction. Keep in mind, we always take sound directed from source to observer. So I'm writing over here, okay? We take sound directed from source to observer. So we have this. And this direction, okay? This direction is taken as positive direction. So direction from source to observer, okay? This is taken as positive direction. So this is to be noted, okay? Now what do you find? V naught is 0, okay? So we have this. And it is emitting sound, okay? Of frequency F dash. And the observer is listening apparent frequency F double dash. So we have this. Now what do you find? In previous case, okay? We have this. The wall, okay, is moving with velocity V naught. So we have this, okay? So I'm writing over here. The source is moving, okay? Now we have this. The source is moving with velocity 0.33 meter per second, okay? It is in SI system. So we have this. Clear? And the speed or the velocity of sound, okay? V equals 330 meter per second from the question, okay? So we have this. It is 330 meter per second. So as I said earlier, we are going to generalize this expression, okay? And this problem. So we have this formula. Here we have this formula, and this is for source moving towards observer and observer moving away from the source. Now what we do, we are going to generalize this expression in this problem, okay? So we have f double dash, okay? So we have this equals f dash, and the velocity of sound is v, and v naught is 0, okay, minus 0, divided by v minus vs, because we have positive direction, okay? We have this positive direction. Clear? This is the positive direction, and we can see v naught vs, okay, is positive. So we have f dash, okay, v divided by v minus vs. So we have this. Now let us find this, okay? So f dash and v is 330 divided by 330 minus 0.33, okay? So let's find this. So we have 329.67. We have this. So we have 1.001 f, okay? So we have this. Therefore, f double dash equals 1 point. So we have f dash, okay? Sorry, this is f dash 0, 0, 1 f dash. Let's call it equation 2. Now we have f dash, okay, from equation 1 equals 1.001 f. So I'm writing equation 1, okay? We have this. F dash equals 1.001 f. This is equation 1. So what do we do now? From 1 and 2, okay, we can write f double dash equals 1.001 and f dash is 1.001 f. Therefore, f double dash equals 1.001 whole power 2 times f. So we have this. Okay? So let us call it equation 3. So this is equation 3. And as I said earlier, okay, frequency and wavelength are inversely proportional to each other. So we have this. Therefore, we can write 1 by lambda double dash, okay, equals 1.001 whole power 2 times 1 by lambda. So we have this, okay. Therefore, we can write lambda double dash divided by lambda, okay. This equals, I'm simplifying, okay, 1 divided by 1.001 whole power 2. So we have this, okay. Now let us do, okay, we are going to simplify this expression. We have this lambda double dash by lambda, okay, equals 1 by 1.001 whole square. Okay. So we have this. Let us simplify this expression. Okay. So I'm writing in this way. 1 minus lambda double dash by lambda equals 1 minus 1 by 1.001 all square. So the left hand side gives me lambda minus lambda double dash by lambda equals. Now let us find the right hand side. Okay. So we have this 1 minus. Okay. Or let me write directly. Okay. So we have this 1.99. Okay. So we have this times 10 power minus 3. So I can write in this way. Okay. Directly. Lambda minus lambda double dash by lambda equals to times 10 power minus 3. So we have this. And we can write delta lambda. Okay. So this represents change in wavelength. Okay. By lambda equals 2 divided by 100 times 10 power minus 1. So we are asked to find, okay, we are asked to find how much in percent does the wavelength of sound change on reflection from the wall. So we are asked to find percentage change in wavelength. So I'm writing in this way. Okay. Percentage change in wavelength. This equals, so we can see from this equation. Okay. 0.2%. So we have this.